Alright, today we will be talking about soft margin classification in SVM. In the previous lecture we had discussed about using kernel functions or the kernel trick to solve for the case when the data is not linearly separable. So there the idea was that you project the data to a high dimensional space where the data is linearly separable. But in today's lecture we'll be looking at a different way of solving the same problem. When the data is not linearly separable, we use something known as soft margin constraints, and we add those slackness, or we add some relaxation, which allows us to still use the trivial SVM or this trivial linear SVM that we've been using. So the idea in this case is that the data seems to be slightly non-separable, where the word slightly has to be taken with a grain of salt. You see that the +1 class, the red class, mostly all the points are correctly classified given these given this hyperplane, separating hyperplane, and these two margins. And so you see that this particular blue point, which is not shaded, seems to be wrongly classified. And for the red case, we see there are two types of examples. One example which is on the wrong side of the margin, but is still correctly classified, because the classification is based on which side of the separating hyperplane you're on. And then there is a point which is on the wrong side of the margin. So this particular point is indeed wrongly classified. The idea is that we can still use the linear SVM without projecting to higher space, and the simple way to do this is to allow some slack. The literal meaning slack means to give you some amount of sort of freedom, or let's say to give you don't need to be very stringent on set of conditions. So some slack psi of I for the ith example, or add some amount of loss for each amount of misclassification, or some amount of penalty. So the idea is that we don't want such points. We ideally want the separation to be as perfect as we'd been seeing earlier in the case of fully linearly separable data. But if that is not possible, and we don't want to resort to projecting the data to a higher dimensions, as in this case, you realize that a couple of examples here and there don't necessarily mean that we have to project it to a higher dimensional space. It may make sense to just allow for some of these sort of errors, or cut them some slack. So we define this parameter psi of I. It looks like epsilon. You can call it either epsilon of I or psi of I, which we define as the distance from the margin. So we look at three such examples, and we see that for this blue example, the distance from the margin is psi of I. Of course, we don't look at the distance of the margin for all the correctly classified points, or all the points which are on the correct side of the margin. Basically, we look at we calculate this quantity psi of I as the distance from the margin in the wrong direction. Now we look that there are different kinds of zones in which points could belong to, and I'll be illustrating these zones with the help of the +1 or the red class, but the same things hold for the -1 class as well. So the first zone is this particular highlighted zone. Now the points in this particular zone are correctly classified, right? You had yi equal to +1 for all of these points, and w dot xi plus b is also greater than equal to 1. Since this particular line hyperplane is wx plus b equal to 1, anything on this side is greater than equal to 1, right? So do we need to cut some slack for these points? No, because these are already perfectly classified, right? So we don't need to introduce any loss or any penalty for these examples. So thus we say that epsilon or psi I for the ith examples which belong to this zone are all zeros. The next zone which is important is to look at the points lying on the margin. So if we look at these points which lie on the margin, so for these we know that yi times wxi plus b equal to 1. So since this is wx plus b equal to 1 and yi is 1, so yi times wx plus b equal to 1, and for these, the blue points, yi is minus 1 and wx plus b equal to minus 1, and if you do yi times wxi plus b, that again becomes 1. Again, do we need any loss for these points, or do we need to introduce any slack? No. These points are already the support vectors and we don't need to do anything for them. They're already well classified. And now we come into the more interesting zones. Zone 3 is where yi multiplied by wxi plus b is less than 1, right? Yeah, we'll come to that. So we're looking at points in this particular red area, and these we're looking only for the red points. Don't look at this blue point for now. So when we look at this particular red point, what we say is that this point is correctly classified, because the classification is decided based on which side of the separating hyperplane you are, and this is on the correct side of the separating hyperplane, but it is on the wrong side of the margin, right? So we say that this particular point will be cut some slack or will be penalized by an amount psi of I. In this example, psi of I will be something between 0 and 1. And the reason it is between 0 and 1 is the following. The equation of the margin, the top margin, is wx plus b equal to 1. The equation of the separating hyperplane is wx plus b equal to 0. And the equation of this particular line is wx plus b equal to 1 minus epsilon of I. Psi of I, sorry. If you were to keep psi I equal to 0, then you reach the separating hyperplane. So at a distance of epsilon psi I from the margin of the positive examples, you have this particular red point, right? So the amount of penalty that you're going to be putting for this particular example is psi of I, right? And then we come to zone 4. Again, we're looking only at the red points and not the blue points. Now this particular red example is incorrectly classified, right? Because yi, ground truth yi was plus 1 and this is predicted as minus 1, right? Or the other way to look at this is that yi, which is the ground truth, is plus 1, but wxi plus b is negative, because this particular separating hyperplane is wx plus b equal to 0. Anything on this side is wx plus b less than 0. Thus yi multiplied by wx plus b is less than 1 in this case. It's negative in fact in this case. So the point is incorrectly classified and you want to put some penalty on this, right? And basically the kind of penalty you want to put for this point in zone 4 should be higher than the penalty you put in zone 3. So what you're trying to say is that you penalize the points, or the points which are not on the right side of the margin, in proportion to the distance from the margin, right? So the point in zone 3 would be penalized less, whereas point in zone 4 should be penalized more. But in both the cases, you see that we come up with this equation of the point, of the line where this point, or the hyperplane on which this point lies, is wx plus w dot x plus b equal to 1 minus epsilon of I. Sorry, this should have been xi. Right. So essentially what we're trying to say is now that we keep everything the same as previous, but we just change the objective. The earlier objective was just to minimize half square of the norm of w subject to the constraints yi wxi plus b is greater than or equal to 1. So this should have been xi, because you're looking for all the examples. And now what we are saying is that we are putting a penalty proportionate to the amount of you're doing. This point is not obeying the constraints or not obeying the margin, right? Proportional to that and multiplied with the constant c, which you can tune, you change the objective, And you also change the objective, or sorry, you also change the constraints now, that yi times wxi plus b is greater than equal to 1 minus epsilon I. I would request you to pause the video for a minute, think for a second that why does this constraint make sense? Assuming you pause the video, so think of the different cases of the different zones. Let's go back. In zone 1, yi is 1, wxi plus b is greater than equal to 1. So yi times wxi plus b is greater than equal to 1, right? And what did we want here? Right, so we wanted yi times wxi plus b is greater than equal to 1 minus epsilon I. And epsilon I is going to be defined to be 0 because there is 0 distance on the wrong side of the margin for examples in zone 1. We go into zone 2. Again, in this case, yi times wxi plus b will be 1. Again, epsilon of I of the points lying on the margin would be 0. And yi is 1, wxi plus b is 1. Coming to zone 3. Now we saw that the equation of the line passing through this point can be written as wx plus b equal to 1 minus epsilon I, right? So, and we saw that the same thing which we can write for the points in zone 4, wx plus b equal to 1 minus epsilon of I. So we know that now epsilon of I is greater than equal to 0. Sorry, not epsilon, I should be using xi. Xi of I is greater than equal to 0. Xi of I is 0 for all the points which are on the correct side of the margin or on the margin, and xi I is greater than 0 for points which are on the wrong side of the margin, right? So all we are saying is now that we put these constraints that yi wxi plus b is greater than equal to 1 minus epsilon of I. We can equivalently write the dual, which remains again fairly similar, but the only major change that we now get is that the Lagrangian multipliers alpha I were previously just constrained to be greater than equal to 0. Now they're also constrained to be less than equal to c. So that is the only change that we need to make in the dual formulation. Now there's an interesting bias variance trade-off which comes in for the soft margin classification using SVMs, and this will also help us understand better the role that C plays. So I'm going to give you a small exercise. You're given these 4 plus 3, 7 points, 4 blue class and 3 red class. Where do you think we should be drawing a margin? And where do you think we'll be drawing a margin varying depending on the value of C? Right? Okay, assuming you pause the video, thought about this, I'll firstly be drawing for the case of when this value of C is low. So let's go back to the equation again. If the value of C is low, what we're basically saying is that we are paying less of our attention towards this quantity epsilon of I, and we're paying more of the attention to this quantity. So in essence what we're saying is that psi of i's can be arbitrarily large, it can be fairly large, because C is so small we don't really care about the second part of the objective. So we keep a low C. We basically say that there is low penalty for violation, where the violation for the ith example is given by psi I, which means that there will be a high training error because we'll be having a lot of violations in the train set itself, which then corresponds to having a high bias. So if you remember, high training error corresponding to high bias, and high generalization or testing error but low train error corresponded to high variance, right? So if C becomes too low, then this becomes wx plus b equal to 0, this would be wx plus b equal to -1, and this would be wx plus b equal to 1. We're essentially okay with missing out on a lot of violations. In contrast, if we increase C to be a really large number, Then if we go back to the objective, then we are saying that there is a high penalty for violation, which means that you'll adjust the margin in such a sense, in such a way that no point gets violated. So the boundary has now changed, if you notice carefully, and the margin has become much thinner. So the margin is the distance, half the distance between the closest blue and the red point, and this leads to a high amount of variance. So again, two aspects of variance. One, the testing error becomes really high because now there could be some points, there could have been some red point here. In the ideal case, that should have been still predicted to be red, but now it might get predicted as blue and vice versa because the margin has become very thin. The other way to look at variance is that if this particular blue point were to be shifted slightly left or right, the model changes drastically. So the model is highly variant based on the training set that you're giving. So this is the bias variance trade-off that we study in case of soft margin SVMs. Just to summarize, low C means high training error and a higher bias. A high C makes our model very sensitive to the data set, which means that there is a high variance. And you can again, so we intuitively saw what changing the value of C would do to the margin. You could just plug the same intuition and just let maths do all the work for you. So if C tends to 0, then the objective is just minimize half W squared, which is to say that choose really large margin without worrying for any of the psi i's. So you don't care about the violations. All you care about is the minimization of W squared, which is maximization of the margin. And if C tends to infinity, then the objective would be only focused on the violations, which is to choose the parameters in such a way that the violations are really small, which would then force the margin to get really small. A quick question, just to understand, just to check whether you were awake or not. So which of these two is the equivalent of the hard margin? So hard margin SVM is when we don't cut any slack, we don't allow for any of these errors. And if you've been awake all this while, then you would see that the answer is option B, when C tends to infinity, which is what we've seen here. When C is a really large number, then you're trying to perfectly separate out the points without having any slack term. Right, so now there are another interesting thing to notice, the definition of support vectors. For the hard margin case, the definition of support vectors was the points which lie on the margin. But if we go back to the basics from which we introduced support vectors, we were talking about the points which are the important points which support the model. So for the soft margin case, the support vectors will also contain the points which are on the wrong side of the margin, because if those points were removed, the classification boundary can significantly change, because you don't then need that amount of slack to be given, right? So we have three kinds of support vectors. First is the points lying on the margin, which we have already seen. Second is the points in zone 3, which are correctly classified but on the wrong side of the margin. And third is the zone 4 examples which are misclassified. So an interesting thing that you'll see is that as C will increase, the number of support vectors will decrease. Can you think why that makes sense? So I'll not tell you the answer right away. We can keep that either for the discussion session, or you can think the answer on your own. In the meanwhile, I just run through a notebook to clarify some of the things that we've been saying, and we'll see practical example to understand it better. Okay, so we have a smallish data set. As you clearly see that the data is not linearly separable. What I'm doing here is to use the scikit-learn's SVM module, and I'm using support vector classification and I'm giving a linear kernel. I'm not doing any kernelization, that is to say, and I'm varying the value of C, capital C, from 10 to the power minus 4 to 10 to the power 10, right? And then I'm fitting the classifier, and then I'm looking at the support vectors, the decision function, and let's see how they look like. So let's go to the starting. When C is really small, so if you remember, when C is really small, all we care about is maximizing the margin. We don't really care about the number of violations, and thus there'll be a lot of violations, which means that there'll be a high number of support vectors required. So in this case, since there is a lot of violations, we see that the number of support vectors is 100. If we go back and see the dataset itself is the size of 100. So each of the point is now acting as a support vector, which means this is a really stupid, really bad classification. We increase the C a little more. Still all of the points act as support vectors, but now at least you're able to see the margin has reduced to some extent. In the first case, the margin is probably somewhere around here, so it's a huge margin. When we increase C to be 0.1, now it starts looking a little more reasonable. And you see that all of these yellow points and all of these red points are already on the right side of the margin, and they don't act as support vectors. But then there are a lot of these points which act as support vectors, and thus you see that the number of support vectors has reduced. You increase C to 100, and you see ever so slightly the margin is decreasing. And if you increase it a lot to this really big number, then you'll see that the number of support vectors has reduced to 24. And now most of the support vectors are the points which are on the wrong side of the are incorrectly classified also. So now we have probably entered the phase of really high variance, because if you remove 1 or 2 points, you will see that everything has changed. And if I make capital C to be really, really large, and now you see that the margin has become incredibly thin. So another thing which is really interesting about the SVM formulation, especially when you factor in the soft margin constraints or factor in the slack, is that we can write it in a very beautiful expressive format and then use our favorite gradient descent based methods to solve this problem. We know that the objective is minimize half W, norm of W squared plus C times summation over all the penalties, subject to the constraints that yi wxi plus b is greater than or equal to 1 minus psi I. If you just rewrite this constraint, we can write that psi I is greater than or equal to 1 minus yi w dot xi plus b. But we also know that psi I is greater than or equal to 0. We know that psi I is 0 for the points which are either on the margin or on the right side of the margin. Right means correct. And psi I is greater than 0 for all the other set of points, right? So we can then write psi I to be max of 0 and 1 minus yi wxi plus b. You can again work out for the different cases that what psi I would be. So if you look at the points which are on the points which are on the correct side of the margin and they are not support vectors, for them yi wxi plus b would be greater than or equal to 1. So the term which is max of 0 comma 1 minus something greater than 1 would be max of 0 comma negative quantity, which would be 0. So psi I is 0 there. You can just play around with the different zones, and you can just verify your understanding of this, that you can write psi I in this format, which means that we can now rewrite the objective as something like you're trying to minimize this whole quantity, but psi I we can now write it as summation. Psi I we can write a summation of max of 0 comma 1 minus yi wxi plus b over all the n examples plus half w squared, and we just divide both sides by c and we get something, an expression like the following. You're trying to minimize a loss, right, plus there is the regularization term. Now this should look fairly similar to ridge regression or lasso, because there also we had a loss. There we were using the squared loss, and here instead we are using the something known as the hinge loss, and then there's the regularization term. And if we notice carefully the loss, the hinge loss, we can see that it is of the following format. So if we plot yi times wxi plus b on the x-axis, and we plot the loss on the y-axis, the loss is 0 for all yi wxi plus b is to be to be greater than equal to 1. At 1, it changes the value rapidly from 0 to something which is now proportional to the actual distance, right? Or the actual loss, the actual penalty that we want to put. So basically in these zones, we have the points which are on the correct side of the margin or on the margin. So equal to 1 is when we have the point on the margin, and all of these zones here are the points where we are on the wrong side of the margin, and that's why there is a penalty imposed on those points. Now if you look at this particular form of the loss function, you would see that, okay, so we can again just verify the loss function for the different cases. As I was mentioning, for case 1, if the points lie on the margin, then yi wxi plus b is equal to 1, and thus loss of the ith example is 0. Case 2, if it is on the correct side of the margin but not on the margin, then the loss is 0. Case 3, it is yi times wxi plus b is less than 1, so there is a non-negative loss. If we talk about the hinge loss, it's convex, as you saw in the visualization. So you could always draw 2 points on this curve, and the curve would always, the line joining those 2 points would always be above the actual curve. But the hinge loss is not differentiable, specifically because of the discontinuity that occurs at yi times wxi plus b equal to 1, and we could still compute the subgradient as we did for the case of lasso. So that's how you could still easily solve SVM using the standard optimization framework. And you can also then sort of make a claim that the SVM loss is convex, because the hinge loss is convex, as we have seen. The penalty term is convex, since that is of the format half w squared, and when you add 2 convex functions, you get another convex functions. So thus the SVM loss is convex, which is really good because it allows you to then apply a lot of techniques which can leverage the convexity. So with that, we'll end this particular lecture. Thank you.